Hello, welcome to the second to last week of quarter 3 in physics. Today we're going to learn about the eye and then lenses and how if your vision needs a correction, which type of lens you are going to need in order to be able to see a little better. So first of all, here is the eye. The lens of your eye, light comes into it and bends it, and the goal is to, as it comes in, to bend it so that all the light rays converge right to the retina. Inside the retina, we have things that are called rods and cones. The rods are the cells that react to black and white and dim light, and then the cones are the ones that work in bright light and color vision. Okay, so when people are colorblind, it's because either they're missing some of those cones or they don't function properly. The lens is a transparent piece inside your eye that has curved sides so that it bends the light right to the retina. When everything works perfectly, they meet at one specific spot on the retina. It starts activating those rods and cones, sends signals to your brain through that optic nerve, and turns pictures into what you see in your brain. It doesn't always work right. Okay, so if you are somebody that needs glasses or contacts in order to correct your vision, there's kind of two ways to express your eyesight. We use an eye chart, and you guys are going to try this in lab later this week. 20/20 is what they deem perfect vision. Okay, if you are 20/200, what that means is what perfect vision people see at 200 feet away, you have to be 20 feet away. If you were 20/300, what perfect vision people can see at 300 feet away, you have to be 20 feet away. So you have to be much, much closer. If you have a prescription, okay, they put it into more of a decimal form. So instead of 325, they put 3.25. But it means the same thing as up here. If your prescription is a negative 3.25, the negative is telling you you're nearsighted. And the 3.25 means what perfect vision people can see at 325 feet, you have to be 20 feet from it. So you have to be much, much closer. All right, so what we are going to be looking at with lenses, it is called refraction. It is the bending of light. Lenses are transparent. When light hits them, it goes through, but the curve of the lens causes it to bend as it goes through. This is different. If you remember, mirrors reflect light, which means it bounces off. Now lenses are going to refract light, which means it goes through and bends as it does. If you need contacts or glasses, it's one of two reasons usually. Either you're farsighted or you're nearsighted. Farsighted, if you have a prescription with a plus in front of it, what farsighted means is you can see far away, but you have a hard time seeing up close. So usually you need reading glasses, something to help with blurriness when you're reading things up close. This can be corrected with a converging lens. Okay, so what's happening in your eye, if you are farsighted, the light comes into your eye, hits your lens bends it, but instead of it making it hit directly on the retina, it doesn't bend it enough so that it would hit kind of at a point way back here, which means when the light rays hit the retina, they're all spread out. Spread out light rays equal blurriness. All right, what you need is a lens in front of your eye's lens that bends the light a little bit. When then it hits your lens, it bends just the right amount, so it corrects your lens of your eye. So it puts a second lens in front of it to make those light rays bend enough to hit directly on the retina. All right, so if you are farsighted, the light converges to late in the eye. It would hit way back here if it could. We need to move it up. We need a lens that makes light rays bend in and come together sooner. So we need to bend the light a little bit more in so that when it hits your lens, it perfectly hits right at the retina. What that is it's called a converging lens. A converging lens makes the light rays that travel through them converge or come together. So when the light hits it, it bends it in so that they come together. These ones, you're going to see two lenses today. These ones are thicker in the middle. So they're going to be a fat center of the lens, and then they get thinner towards the edges. Okay, I'm going to put this on the camera, and what we're going to do is we are going to look at a converging lens, and we are going to look at something that's far away, we're going to look at something right at the focal point, and then we're going to look at something up close. Alright, so camera is coming up. I'm going to move it over to my station over here. I'm going to kind of put a copy of my notes right here, and then we're going to use what is a converging lens. So if you see the converging lens, it is thick in the middle, and then towards the edges, let me just put autofocus on here. It is then thinner at the edges. So it's got a thick, fat middle, thinner at the edges. All right, I'm going to flip this like this, and when I hold it far away from something, you'll notice the words that I run over, they're upside down. So far away from something, it is going to be inverted. As it moves closer to the words, you'll notice a point where it gets super blurry, where you no longer can read those words. It's just kind of flashes of light. You have found the focal point. But if you push through the focal point and get even closer, what you'll see is it becomes upright and it gets magnified. This would be a magnifying glass. If you have one at home, if you can look at it, you'll see that it's fatter in the center. All right, so converging lens can do three things. When it's far away from something, it makes it upside down, inverted. When you're right at the focal point, it makes everything blurry. And then when you push through the focal point, it flips it back upright and it magnifies it larger. All right, so filling in those three, inverted, upside down. When it's far away, it gets blurry when you find the focal point, and when you get up close, it flips it back upright so you can read it again, and it makes it larger like a magnifying glass. A magnifying glass would not be very helpful if it was always upside down, so when it gets close with a converging lens, it makes it bigger and upright. All right, here are our diagrams. Okay, so it's going to be set up really, really similar to mirrors, which everybody likes a lot, right? So you're going to need to measure out the starting distance of the arrow. A reminder, your starting arrow always goes over on the left side. You need to know P, which is how far away it is from the lens. I measured this to be 6 inches. Then you need to know HO, which is the height of your starting object. I measured it to be 1. And then you need a focal point. I just picked a focal point of 2, and converging, remember light hits a lens, it goes through but it bends. It's going to bend in line with the focal point on the right side. Okay, so for a converging lens, the two light rays, once again, I'm going to go back to my same two colors. First color is going to be red, and then the second light ray will be in blue. The first light ray, if you can find yourself a straight edge, you are going to draw a straight line from the top of the arrow all the way to the surface of the lens. Okay? And I made this a converging lens. I've made my arrows in that direction. It's supposed to symbolize that it gets fatter in the middle and thins out at the edges. All right, straight line until you hit the surface of the lens. It's a lens, it's transparent. When light goes through, it bends the light, and it bends it in line with the focal point on the other side. So it bends through the focal point. Okay, so that's light ray number 1. Straight line to the surface of the lens, and then it bends through the focal point on the opposite side. Light ray number 2 is always exactly the same for any type of lens. It is going to start at the top of the object, and it is going to go through the center of the lens at this dashed line right here, your principal axis. So you're going to start here, you're gonna go through there and you're gonna continue until they intersect way over here on the right side. All right, I don't have a straight edge with me, so it's not gonna look the best, but. Okay, so first line in red, straight until you hit the lens, and then it bends when it goes through the lens in line with the focal point on the right side, because it's converging, coming together. The second light ray, always the same, starts on the top of the arrow, goes through the center of the lens, keep going until they intersect. That intersection point right there predicts the image that you're going to see through your lens. Okay, notice it's below this line right here, it's pointing down. That's because it's inverted. Look at that. When things were far away, they were inverted. And then this is going to be what we call a real image. Anything on the right side, that's what light actually does. It goes through a lens. You can put something there and project it, and it will show up. And you can do this with a magnifying glass. You can find a light and then hold up a magnifying glass, and it will actually project a picture of the light bulb someplace else. You can put up a piece of paper, and you can actually move it around and see that projection. That is a real image. This is also when Q is going to be known as positive. So when the intersection point, the image that we see in the lens, shows up on the right side, you have a real image, and Q, the distance from the image to the lens, is going to be known as positive. Okay, so that is a converging lens, which helps us correct farsightedness, which means you can see far but not up close. So this is reading glasses, magnifying glass, anything that can help you see up close a little bit better. All right, moving on. Most people your age, if you need correction for your eyes, it's because you are nearsighted. And your prescription will have a minus sign next to it if you are nearsighted. This means you can see up close. You can see near, but you can't see far away. It gets blurry the farther away it is. In order to make the correction to your vision, you need a diverging lens. Diverging. All right, so here's what's happening in your eye. And it has different reasons. It can be due to the shape of your cornea. It can be due to the shape of your eye. But what happens is the light, when it hits your lens, the lens bends it too much. So instead of hitting in a nice little spot here on the retina, it hits too near in your eye. So it hits more like in the middle of your eye right there. And the more nearsighted you are, the closer that those light rays are condensing in towards the middle of your eye. All right, so it doesn't bend the light enough, or excuse me, it bends it too much, and it makes it bend so that it hits more in the middle of your eye instead of back at the retina. So what needs to happen is when you have a lens, a diverging lens, it needs to spread out those light rays a little bit. So when they hit the lens, they bend a little less, and they then bend them so that it hits right at the retina instead of in front. Okay, so light converges too near in the eye, so too soon. We need a lens that makes the light rays spread out so they converge later. All right, and that's why there's different prescriptions, because each person maybe needs it to go just a little bit farther back, and that's what the different prescriptions in your lens will cause it to do. Okay, so a diverging lens makes the light rays that travel through them spread out or diverge. Diverging lenses are thicker on the edges, so they are going to have a thick edge. So if you are nearsighted and you have glasses and you pull off your glasses, you'll notice that around the rim they're really thick. Okay, that's a diverging lens. All right, once again, going to my camera, I'm just going to pull up a diverging lens, and then we're going to look. Okay, so I am now going to switch it over to a diverging lens. So with a diverging lens, they have thickness around the edges, and then they get thinner towards the middle. Okay, if I hold it far away from the words on my paper, it's upright and smaller. And as I get closer, no matter what I do, it is always upright. It never flips upside down, and it makes everything smaller. All right, so a diverging lens is thicker on the edges and makes everything smaller and upright. Smaller and upright. Okay, so we're gonna draw the diagram for diverging as well. The only difference for diverging is because when light hits the lens, it spreads it open. So instead converging went this way, diverging is gonna go this way. It lines up with the focal point on the left side this time. Okay, so diverging puts the focal point on the left side, unlike converging on the front of your notes, put it on the right side. Left side means backwards, which means it's negative when we do our math. Okay, so I have this measured out. I started the starting object. I made it start 4 centimeters, that was P. I made it 1 centimeter tall, and then I put a focal point at 3 centimeters, and it's a -3 because it is on the left side of the lens. Okay, for this, we start out the same way. You start at the top of the arrow, you draw a straight line until you hit the surface of the lens. Once you hit the surface of the lens, the light goes through, but it bends as it goes through. When it bends, it opens up, it diverges, and it opens up in line with the focal point on the left side. So as it opens, I gotta line it up. It opens up, bends in line with the focal point on the left side. Okay, so that's the only difference with the light diagrams, is which focal point that you use. For converging, we use the one on the right side because it converges or meets. Diverging opens up, so we use the focal point on the left side. The second light ray is the same for any type of lens. You start at the top of your arrow and you go through the center of the lens at that principal axis. So right through the center. Okay, notice they don't intersect on the right side anymore, they intersect on the left side. This is predicting the image that you see in a diverging lens. Notice the image arrow, the blue one, is smaller than the starting object, the black arrow. So the image is smaller. What you see through the lens is smaller than what it was to begin with. It is upright, it's above the line, it's pointing upward, and this is what's going to be called a virtual image. Light doesn't actually move backward from a lens, it goes through. So when it's virtual, when it shows up on the left side, you have a virtual image, which means you cannot project it. This is also, when you're on the left side, is when Q is negative. Q is negative when the image shows up on the left side, and it's also virtual. Okay, equations are exactly the same as they were for mirrors. So we're going to use those same two equations. The 1 over F equals 1 over P plus 1 over Q. And the HI over HO equals negative Q over P. You guys are good with those equations, so the math will be easy for you for this little unit. And then finally, sign conventions. When you go to do your math, F has to be a positive number when you're using converging, but diverging, because you're using the left side focal point, you have to put a negative sign in front of your focal point. HI, still positive when it's upright, still upside down, it's negative. Q is positive when it shows up on the right side. So when the image, the intersection point shows up on the right side, we have a positive Q. When it shows up on the left side, like this one, it showed up on the left side, that's when Q is negative. And then finally, Q and our images being real or virtual, they kind of match up. When the image is real, it's on the right side, also Q positive. And then, ooh, so sorry. Virtual, the image is virtual when it shows up on the left side, which is also when Q is negative. So those go together, the Q positive with a real image, Q negative on the left side with a virtual image. Okay, from here, you're gonna start working your way through your lens problems. So I'm just gonna help you set up the first couple so that you can kind of see how to measure it out. So once again, I'm gonna go to my camera and use my actual protractor. All right. Okay, so we are gonna do this exactly the same way that we did for mirrors. First thing we have to do is read through it. I have a 1 centimeter tall object, that's HO. It is 8 centimeters from a converging lens, that is P, and the lens has a focal length of 3 centimeters. Okay, you have to get all 3 of those things measured out. So you have to put the starting object 8 centimeters to the left, all the way to the left. So I go to 8, put it right on my converging lens, and go all the way here and mark it at the 0, 8 centimeters. I need it to be 1 centimeter tall, so I start my arrow, 1 centimeter tall, and then from there, I need a focal length of 3. It is a converging lens, which means the focal length is gonna go on the right side. You're gonna use the F on the right side. You are going to run your lines and find the intersection point. Once again, the intersection point, you will measure 2 things about it. You will measure Q, the distance to the intersection point from the lens, and you'll measure, using your protractor, once you've run your lines, you just measure the height of the image. Okay, once you've drawn it out and used your protractor to measure Q and HI, you're then going to repeat that process but use the math. You are going to solve for Q and HI using these right here and your 2 equations. Okay, from there, you are going to repeat this process, but you're then also going to do a diverging lens. Okay, diverging, it has an object 1 centimeter tall, it is 5 centimeters in front of the diverging lens, and it has a focal length of 2. Remember, diverging is the one that gets a negative in front of it, so the focal point is a -2. Okay, I need to measure those things out. Once again, I gotta have a starting object 5 centimeters in front of the lens. So I go to the 5, I measure over, and I make it 1 centimeter tall. And then I need a focal point of 2, but it's a -2 diverging, which means it's gonna come through the focal point on the left side. So I need to measure out 2 centimeters to the left. Okay, that's the difference between converging and diverging, where the light rays, how they bend. Converging bends through the focal point on the right side. Diverging opens up and bends through the focal point on the left side. For the math, the only difference, gotta put a negative sign in front of F. So instead of 1/2, it will be 1/2. All right, I think that's about it. So hopefully everything went okay, and make sure you send questions my way. Thank you.